Hello students, in this video we'll begin our discussion of the topology, the metric topology of the real line. We say that a subset omega, which is a subset of R, is an open subset. And open is relative to a topology with respect to the metric topology generated by the distance function d of x and y is just the difference between x and y in absolute value, right? That defines the metric. If for any a in omega, there is a delta of a positive real number, such that n delta a of a is contained in omega, where in general n epsilon b is the set of x in R, such that x minus b, which is just, of course, d of x and b, is less than epsilon. Okay, in other words, these are just neighborhoods of the point b, right? So this is an epsilon neighborhood. This is an epsilon neighborhood of b. And of course, geometrically, it's obvious what this epsilon neighborhood looks like, right? So in other words, what does it mean for a set to be open? It means that if I have a point in that set, so let's say here's the real line, for example, and I give you a point in that set, let's say that's the point A, then what I can do is I can find a neighborhood, so that's going to be A plus delta A, and that's going to be A minus delta A, such that that whole interval over here, that whole neighborhood, is contained in the set omega. So it's stuck, there's an interval that's stuck inside omega, okay? And so that's what it means for a set to be open, okay? Later on in further videos, we'll discuss what it means to be closed, and then we're going to see that open and closed sets together don't give you every single subset of R. They give you special subsets, and we'll have to enrich those classes to get more sort of intricate topological sets. All right. So let's do the standard propositions. And so here's the standard proposition for these open sets. Proposition: if, let's say, U alpha in A is an arbitrary collection of open sets, then the union over alpha in A of U alpha is also open. Okay, that's the first proposition. And so, of course, the proof of this proposition is straightforward. How do we do that? Proof: let A be in the union over alpha in A capital of U alpha. And that means that there exists, then, A is in U alpha tilde for some alpha tilde. And that means since U alpha tilde is open, then there exists, since U alpha tilde is open, there is an n delta A that's contained in U alpha delta tilde, some delta alpha delta A greater than 0. This is because by definition U alpha tilde is open, and therefore this n alpha tilde n delta A is also a subset of the union over alpha and A of U alpha, because it's in one of them, right? And that says it's open. That's what we want. And now the harder part of the proposition, there's another proposition over here. So the next part of the next proposition for open sets. So in other words, this is a great proposition. This is like the arbitrary union. So the arbitrary union of open sets is going to be open with respect to this metric topology, and in general, actually, for that's a generic property of topological spaces. Okay. The next proposition is this: is that if U1 through UN, there's a finite list now. It's a finite list are open. Then so is U1 intersect UN, okay? So unlike unions, the arbitrary union of open sets is going to be open, but with intersections, it's only the finite intersection of open sets is open, okay? And of course, how are we going to prove this? Proof. Let's let A be in U1 intersect UN. And then what we can do then is then that says that A is in UI for all I between 1 and n, like so. I can find, therefore there are delta I A such that delta what? Delta N I A is contained in UI, right? And then what I'm going to do is I'm going to let delta be the minimum of these delta IA. So let's set delta A to be the minimum of this finite set. So this minimum is going to be greater than 0. Okay. And then if that's the case, then what can we say? Then certainly it's the case that N delta A is in U1. It has to be in U1 because the delta is smaller than the delta A1, so it's a smaller interval, right? So since delta A is smaller than delta 1, that interval, that neighborhood is a smaller interval. So since delta 1A was in U1, therefore delta A is going to be in U1, and the same thing is true for all of them. Okay, and that proves, of course, that I've just found a subset, actually. This is going to be a subset, not in, right? It's a subset of that. And that proves that the finite intersection is going to be open, right? So one other observation to make is that I'll prove it sort of geometrically and let you fill in the details of this. It's actually a really elementary thing to do. If I just give you an open interval over here, for example, like A to B, okay? Then I need to show for every point, to show that the open interval is open, I need to show that for any point inside this open interval, any point inside there, x, that there's a neighborhood inside here. Well, if I just look at the distance from x to b and the distance from x to a, I know that if I cut that distance, whatever the smaller of those distances, if I cut that distance in half, then that interval will be contained in the open interval. So that's a rough sketch of how you would prove an open interval is actually an open set. So to summarize, open set means that for any point in the open set, there exists a neighborhood, and basically like looks at an open interval, right? A neighborhood of that point that's also contained. And these neighborhoods are actually open neighborhoods by virtue of the fact that it's less than epsilon over here in the definition. Okay, so these are open neighborhoods. And of course, the open neighborhoods are just open intervals, right? And so now we're saying that this definition of openness implies that the arbitrary union of open sets is going to be open. That's clear because once you have one interval stuck in there, it's going to be stuck in all of them. And then the finite intersection of open sets is open because once I have a whole bunch of the open sets that are intersected, I can look at the interval that corresponds to a point that's in each of those things by virtue of the fact that it's an intersection, and I can make that the smallest of all of them. The smallest of all of them will ensure that it's going to be in each and every one of the UI, U1 through UN, as long as that number is finite, because the minimum of a finite number of positive elements is still going to be positive, whereas if it's an infinite number, I can achieve 0. And this gives us our first introduction to the topology of the real line. And so now in general, we can say what a topological space is. A topological space is a set, call it X, with a collection of subsets such that the empty set and the space are always in the topology. Arbitrary unions are in the topology of elements in the topology, and finite intersections of elements in the topology are in the topology. So this proves actually, these two propositions together prove that the real line with this metric topology is in fact a topological space. Thank you very much.